Great. Thank you for your attention for the announcements. Let's get into it then. Our last 3 topics on the list, there's only 3 topics left, and they are all about power series. Power series is super important. Actually, very important just sort of like in our course, but also like really important in the history of mathematics. When power series was discovered, it sort of immediately led to kind of a big revolution of how people thought about calculus and about even just more generally how people thought about continuous functions. Like the idea of a power series is super powerful, no pun intended, and like caused when this came about, caused everybody to like reevaluate some very basic things about mathematics. So super important, and I will try to get into a little bit of what's such a big deal about it as we go. But maybe we'll just start talking about what it is. So a power series is some kind of, I would describe it as like an infinite polynomial. And generally speaking, they look like a polynomial with, coefficients just like any polynomial, but the degree just kind of like goes up and up forever. That's what I mean by infinite polynomial. Usually when I write a polynomial, I like to start with the highest degree term, but because this one is going to be infinite, you sort of have to write it starting with the lowest degree term. So I'm going to write it this way. C2x squared, C3x cubed, etc. This is the general format of what a power series is, where those c's are just some kind of coefficients. So you can think of this, it's basically a polynomial, only it goes on forever. It doesn't have a degree where it sort of ends, but it just keeps on going. All right, this is called a power series. And we can think of this, so you can also write this, in the series notation. This will be written Cn times x to the n. All right. Now this is an unfortunate technicality. When you write it as a sum this way, which we are often going to write it this way, you have to start the n at 0. Like usually when we do a series in this class and in our book, they usually start n at 1. But because of the way a power series works, you always want to start with x to the power 0 here. And so a power series, when you write it as a series, it is almost always written as n starting from 0 to infinity. This is sometimes a source of slight confusion because we are used to starting with n equals 1. Mostly it doesn't really matter. But anyway, this is what a power series is. So it's a series, and so you can study these things the way that we have discussed over the past couple weeks. It's a series. But what's sort of special about it, it's a series, but we can also plug in different x values and see what you get, right? So it is a series. It is like a sum of infinitely many things, but it's also something like a function where you can plug a value in for x and get some kind of an answer. We can plug in different x values, and so it makes a function. That is, you plug in some x and you get some answer out. Although sometimes the answer is just, it diverges. Like for certain x's, you might get an answer because you plug in some value for x and this actually adds up to something. But sometimes you might plug in a value for x and this adds up to infinity or something like that. So it makes a function, but for certain x, it may diverge. All right, for certain x, it might diverge. That's what that says. And for certain x, it may converge. Like actually in this example here, you can tell just based on the format here, if I plug in x equals 0, actually this will always converge. If I plug in x equals 0, then all of these guys become zeros, and that's the whole answer, just C0. So every power series converges when x equals 0, but it may, for other values of x, really it's not clear if it's going to converge or not. It would depend on specifically what all these coefficients are, whether it's going to converge or not. All right. Two big questions that we are going to ask about power series. Two big questions. The first is really what we're going to focus on for today, and that is, for which x does it converge? And then the second question is sort of, what does it add up to? Like, which function? This maybe is a vague question, but I'll let you know what I mean more specifically than that. But if I give you a series where I actually tell you what these various coefficients are, can you tell me for which x does it converge? And furthermore, for those x where it does converge, what does it actually add up to? And does it add up to some recognizable function? This is what we're going to talk about eventually. But anyway, for now, let's talk about the first question here. For which x does it converge? I want to do an easy example and then some less obvious examples. So the easiest example is when all of the coefficients, all the c's equal 1. Right? Up here, the general format is like that, where the c's could be any numbers. So let's just, to make it real simple, let's imagine that all the c's are 1. So that means what I'm talking about is this power series, 1 plus x squared, x cubed, etc. I'm using 1 for every coefficient, all right? Actually, I can think of an easier example would be when they're all 0. That's not really, that's too simple to be interesting. But when they're all 1s, that's something that's interesting enough. Not too simple, but it's still simple. All right. This, of course, I could also write as a sum, just sum of x to the n, where n starts at 0. All right. For which x does it converge? Actually, you look at this, and in this example, I actually recognize what that is, or this is a familiar type of series. This actually is a geometric series. Because each term divided by the previous one, you always get the same answer. And in this example, that answer is x, right? If I do x divided by 1, it's x. If I do x squared divided by x, that's also x. X cubed over x squared is also x. So every ratio of the next term divided by the previous one is the same every time, and it's x every time. So this is a geometric series, and in this example, I can say what's the a and the r. Anybody remember how to do this? What's the a in this case? You remember? It's 1, yeah. How'd you get 1?
That's the first.
Yeah, the a is always just the first term of a geometric series, so a is 1. And the r is the common ratio of the terms. It's always the next term divided by the previous one, and this is what I was just talking about. That, in this example, is x. All right? So this is a geometric series, and if I'm trying to answer this question at the top there, for which x does it converge? Actually, we already know the answer to that question for a geometric series. It converges, just because this is a geometric series, converges when absolute value r is less than 1, right? That's the rule for a geometric series. And so in our case, r equals x. So this, the same way, another way of saying that is just, it converges whenever absolute value of x is less than 1. And actually, so this is the answer to that question, for which x does it converge. Actually, you'll see as we do other examples, we're going to express this as an interval. So the convergence, this is a general fact about power series. The convergence can be expressed as an interval and we've already really done the work for it, but it's just a matter of taking this right here. Absolute value x less than 1 is the same as this. When I say absolute value of x is less than 1, that just means x is between -1 and 1. All right? And thinking of it as an interval then, we say this is called the interval of convergence. Interval of convergence is, in this example, the interval from -1 to 1. It's just this, but I'm writing it as an interval, the interval from -1 to 1. And I hope everyone remembers when we write intervals, I use sort of the roundy parentheses when the endpoints are not included in the interval of convergence, because for a geometric series, it does not converge when the absolute value of x equals 1. It's only when absolute value is strictly less than 1. All right, the interval of convergence. This I'm also going to write IOC for interval of convergence. All right, in this example, it is -1 to 1. And so that means if I'm plugging x in this interval, if x is in this interval, it's going to converge. If not, it's going to diverge. All right? And actually, in this case, so as far as like these two questions, we just answered this one. For which x does it converge? In this example, it converges when x is in the open interval from -1 to 1. What does it actually add up to? This is also something that we can easily say in this example, because we know there's a formula for the geometric series, what it adds up to. So for this case, it sums like, if f of x is this power series plus dot, dot, dot. Anybody remember the formula for what a geometric sums to? This is, I'm sure somebody must remember. What the geometrics in terms of a's and r's? Yeah? Yeah, that's the a over 1 minus r is what it adds up to. So this adds up to a over 1 minus r, but we already decided what all of those things are. A was 1 and r was x, so it's that. All right, so this is that sort of second question that we like to answer about power series. This actually equals 1 over 1 minus x. This is very strange, but let me just write that again. This power series actually adds up to that. And I will just say when x is in the interval -1 to 1. All right? Strange but true fact. You can add up one of these like infinite polynomials. It somehow, you could say it simplifies to that or something. Like somehow it adds up to this, which is very strange. But this is kind of what I meant when I said we're going to ask this question. What does it add up to? Like which function? In this example, this infinite polynomial-like thing actually adds up to a normal-looking function. And this is, in my opinion, there's something profoundly weird about this. And this is actually why, like I say, power series kind of caused a revolution in the way that people think about functions. Because what I immediately start to think about is, okay, this function can be written like that power series where all the coefficients are 1 every time. What about like some other, pick your favorite other function. Like for instance, I could wonder about like, what if I want to talk about sine x? Is it actually possible to write sine of x in some way like that as a bunch of, and some kind of infinite polynomial? And if that is possible, then what are the coefficients? That, like, if you use 1 every time, you get that. But what if I do, I'm scribbling, what if I do something else? Don't use 1 every time. What if I use 1s and minus 1s? What does that add up to? What function does that make? Or what if I use 2s every time? What function does that make? These are the big questions that people started asking. And if you didn't know about, like before power series existed, nobody even thought about this at all. But it gives you like another way of looking at functions, or another way of thinking about functions. Like this function here, once you know that it can be written in this way, that actually tells you a lot more stuff about what that function is like. Anyway, this is where we're going with all of this. But for today, we are just going to talk about finding the interval of convergence. So I have a couple of examples, and then I have one for you to try. So here is another. This is a much more complicated power series, right? The one we just did was just 1 every time. This one, the coefficients look like 1 over 3n every time. And then you, of course, multiply by x to the n. Now, I want to avoid, of course, if you use n equals 0 here, you get 0 in the denominator, which is bogus. So I'm going to just consider starting with 1 here. All right. So this is a power series where like there is no constant term at the beginning. We start with just x to the power 1, and it equals whatever it equals when you plug these numbers in, right? Actually, if I were just to write out a few terms, the n equal 1 term would look like 1 over 3 times x to the 1. The n equal 2 term would look like 1 over 6 x to the 2, 1 over 9 x to the 3, and so on, right? That's what you get when you plug in various values of n to that. And the question is, you could ask, what does this actually add up to? Although we're not gonna talk about that's a harder question. But for now, let's just talk about for which x does it converge. It turns out this convergence question is always about an interval. So we're going to end up finding an interval as our sort of final answer. All right, let's see how to do this. In all cases for problems like this, we are going to use the ratio test. The ratio test is the most convenient type of sort of mechanism to answer this question. So this will look weird. Hopefully you've had a chance to look at the homework for tomorrow, which involves doing the ratio test quite a bit. This is like that, only, well, like I said, a little weird, but let's do it. So ratio test is all about this L, which is lim n goes to infinity of absolute value an plus 1 over an. All right. This is always what the ratio test involves, and it has absolute values in there. Now, in the examples that we have done last time and in the ones on the homework, there's usually one step at which you just say like, okay, I don't have to care about the absolute values anymore. You ignore the absolute values. Actually, when you're doing these problems, the absolute values will never go away entirely. You have to keep them around. I think always, like in every example when you're doing this, you do need to consider the absolute values. But anyway, let's just plug everything in here. I have absolute values and then an plus 1 over an. I'm going to do an plus 1 and then times the reciprocal an. So an plus 1, I read the term up there, but I put n plus 1 instead of n. So it looks like this, right? That's the an plus 1. And then times the reciprocal an. So I'll go times the reciprocal of an. That would be the thing just as written originally, but in the reciprocal. All right. Let's try to simplify as much as you can and then take the limit. So as far as simplifying goes, I would group together the two sort of things, the similar things. I'll put the x's together. I have x to the n plus 1 up top over x, and I'm going to split the absolute values also. And then I also have 3n over 3n plus 1, like that. All right, I just like to put the similar, sorry, not over x to the n. I'm just rearranging stuff so that similar things go with similar things so that I can cancel as much as possible. And we can cancel in the x's part. This is lim n goes to infinity. What do we get when we cancel here? Somebody shout it out. I'm going to cancel. I think just x. Yeah, we have one extra x in the numerator and a bunch of x's in the denominator. We cancel, we get x. And it's still inside the absolute values. Can I just make that x because x is positive? The answer is no, because x is not positive. X could be any real number, and we don't know if it's positive or negative. It might be negative, so you must leave the absolute values there the whole time. The other part, 3n over 3n plus 1. Actually, those 3's can straight up cancel. Then I have n over n plus 1, and I think for that part, I can get rid of the absolute values. This part really is positive because n is a whole number starting with 1, and so this is never going to be negative. Unlike x, which can be any real number. So this, you got to keep the absolute values. The other part, you do not. All right? Now we can do the limit. This x has no n's involved, so this is just going to stay like it is when I do the limit. This over here is going to give me 1. That's because this is a ratio of polynomials. You can divide out the highest power of n that you like, or you can just say they are equal degrees, and so the answer will be the ratio of the coefficients, which is 1. So this right here, I end up with just absolute value x. And that never goes away. I mean, this doesn't simplify. We don't know what x is. X could be any real number, and so that's as good as it gets as far as simplifying here. All right. Now, we are doing the ratio test where the L is absolute value x. And so remember the conclusion of the ratio test? So the ratio test, the rat test, it says converges when L is less than 1, diverges when L is greater than 1, and I don't know when L equals 1, right? That's the statement of the ratio test. And so we can immediately say, so it converges when L less than 1, but I just said L equals absolute value x, right? That whole calculation that we just did is to show that L equals absolute value x. And so it converges when the L is less than 1, which is to say when the absolute value of x is less than 1. It diverges when the absolute value of x is greater than 1. So it diverges when absolute value x greater than 1. And we don't know when the absolute value of x equals 1. So there's actually still a little bit more work to be done. But maybe I'll just say this thing where it converges, just like before, I'm going to write it like that. Instead of absolute value x less than 1, that's the same as x is between minus 1 and 1. So it converges in this range. It diverges when x is outside here. The only unknown situation is when L equals 1. That is to say, if x actually is 1 or if x is negative 1. So we must, you always have to do this as sort of like a technicality at the end. We must check the endpoints as a special case. So we have the endpoints, I mean the endpoints of this interval. This is the interval from minus 1 to 1. But we don't know, because the ratio test is inconclusive, when we're actually talking about 1 or actually talking about minus 1. So we check the endpoints. And these you just have to do, leave some space here. We just have to check these specifically. Does it converge in each of those two situations? And these are also not so hard to do. We just have to remember what we started with was this, x to the n over 3n, right? Now, if I'm using x equals 1, you just plug in x equals 1. I get just 1 over 3n. And then you ask yourself, does this converge or diverge? And you have to, in these steps, hopefully it's something that just sort of looks familiar to you, or else you may have to use one of your convergence tests, the integral test, or whatever. This one actually looks pretty familiar to me, though. I would, if I factor the 3 out, it looks like that. You can pull out a 3 from the denominator. It's a weird-looking summation sign there. It's a little better. What about sum of 1 over n? That is the harmonic series which diverges, right? Or you could say it's a p-series, p equals 1, all right? So this one diverges. These special cases, checking the endpoints, you just plug the value in, and then hopefully it looks like something that you've seen before, and you know if it diverges or not. All right, and what about x equal minus 1? For this, again, I'm going to plug the value in. This will say minus 1 to the n over 3n. Again, if I pull the 3 out as a 1/3, this is now minus 1 to the n over n. And that one, anybody recognize that? Does this diverge or converge? this is now alternating. This is called the alternating harmonic series. We talked about this maybe 2 times ago. You can actually show that this converges using the alternating series test, or this is a standard example. This one converges. If you like, you can use the alternating series test. Although I don't want to go through the details here. This is the alternating harmonic series, and it converges. It converges actually to the natural log of 2. Like we talked about this example in some amount of detail. All right. We've actually finished everything that we need to do for this problem. We should just summarize the answer. So the answer is basically the interval of convergence is this, but then we also checked the endpoints. We found it diverges at 1, but it converges at -1. All right, so my final answer then is, so it converges, for which x does it converge? It converges for x like that. All right, x between -1 and 1, that's what we found in the previous step. We just, at the end here, we found that it also converges when x equals -1, but it does not converge when x equals +1. So that's why there's a less or equal here, and there's a straight up less than here. All right. If you want to write that as an interval, the interval of convergence is, I would write it like this. With the square bracket at -1, that means we are including the -1, but not including the 1 in my interval. All right, this is how we do it. It's basically just the ratio test with lots of extra sort of weird stuff going on. All right. I got another one, and then I got one for you to try. Yes, let's try. This will be very similar looking, but actually the answer turns out to be quite different. How about x to the n over 3 to the n? The one I just did was 3 times n on the bottom. This is 3 to the n on the bottom. What difference does it make? I would say, makes quite a difference. But let's work it out. We are going to do the same thing. You don't have to think a lot to start. We're going to do the ratio test. So do the L thing and then work out the limit as best you can. So I am doing the ratio test. It says lim absolute value an plus 1 over an. All right, and we're gonna plug in, work it all out. So an plus 1, I plug in n plus 1 instead of n first. So I get x to the n plus 1 over 3 to the n plus 1. And then I'm going to go times the reciprocal of an. That would be the original term as written, but I'm going to do the reciprocal. So 3 to the n up top, x to the n on the bottom, like that. All right. I would rewrite this to group things sort of together with their friends. I put the x's together. I put the 3's together. And then we can cancel as much as we can in each of these. In the first one, when we cancel, we just get x left over. X like on top, there's one extra x. And the second one, there's one extra 3 on the bottom. So this, when I simplify, is just absolute value x from the first part. And then the second part is 1/3, right? There's an extra 3 on the bottom. And actually, I don't need the absolute values around that, because this part really is positive 1/3. That's all there is to it. All right. And then finally, we take the lim. Actually, the lim in this example, the lim is totally uninteresting because there's no n's at all right here. So when I take the limit, just like nothing happens, and I just get absolute value x times 1/3. That's the L. All right. All right, we're getting there. This is kind of like the first step. And the ratio test says that it converges whenever that is less than 1. So it converges when absolute value x times 1/3 is less than 1. And I'm going to try to write this as an interval. This is a little weird, but it always goes the same way. When I have absolute value something less than 1, to write it as an interval, I throw like a -1 and a 1 around it, this time with no absolute value signs, like that. This is always how we turn an inequality with an absolute value into a sort of double inequality with no absolute value. All right, and then right there in this inequality here, I'm going to multiply through by 3 to like sort of solve for x, get x all alone in the middle. Multiply through by 3 gives me that. All right. So this is basically the interval of convergence, although, just like before, we need to check the two endpoints as special cases. But that'll pretty much do it here. So now we check the endpoints. They are x equal 3, first of all. So I'm going to write the original series again, x to the n over 3 to the n, but I'm going to plug in 3. So it becomes 3 to the n over 3 to the n. Those cancel, of course, and you get 1. So this is the sum of 1. That's, 1 plus 1 plus 1. What do you say? Does this converge or diverge? Somebody say it. 1 plus 1 plus 1 forever? Does that converge? Nobody wants to say it. Is it because you don't know it, or you just don't want to say it? I hope it's because you just don't want to say it. This diverges. If you add 1 plus 1 plus 1 forever, it does not add up to something specific. This diverges here. This is one of the first examples that we ever talked about, right? Adding 1 forever. Diverges. Okay, so that was one endpoint. I have to check the other endpoint. X equal negative 3. All right. So this is going to be minus 3 to the n over 3 to the n, right? I'm plugging in minus 3 for x. How can we simplify this? This is slightly weird, but you can do like so. Sort of pull that nth power out. This is a legal operation to do with exponents. If I have two nth powers divided, that's the same as a single nth power where they're divided like that. But now I can simplify on the inside. Negative 3 over 3 is just minus 1. So this is the sum minus 1 to the n. So this is like, I'm starting n at 1, I guess. So this is like this. And this also we have discussed in the past. This also diverges. This is the one where you keep on doing minus 1 plus 1 minus 1 plus 1. That also diverges. All right. So what's my final answer? My final answer is basically just this, right? It's this, and then we also have to check the two endpoints, but we discovered actually it diverges at both endpoints, so they are not included in the interval of convergence. So my final answer is converges. Well, can I just say the interval of convergence is the open interval minus 3 to 3, not including either endpoint, because both endpoints we found diverges. All right. This is how we do it. I got one for you all. See how you like it. This is similar. These are kind of long. I mean, it'll take you a few minutes to work it all out, although it should go pretty much the way that it goes when I did the ones that I did. See how you feel about that. Your job, find the interval of convergence. Feel free to chat with your friends. I know some of you do. Yes, let me set up. How's it going? Yeah, I would say oh, yeah, that's good, yeah. And then let's see, second put the fives together and also put the things together.
Can I have like instance or?
Yes, you're eventually gonna take the ends. Still. But yeah, at this point, I think you just have N on top and N plus one on top. Eventually, you're gonna take the limit of this. This is all good. Yeah, you have to actually incorporate this. You should be like 5.
Do I have to like show that?
You can if you can do it here. Mm-hmm.
Okay.
Mm-hmm. That's good. Here. Just 5. Is it here?
Is that right? Yeah. I forgot it.
Writing, yeah. So there should be a 1/5,
Oh.
and that matters. That will just stay forever. Here you can check those together. Yeah, this all looks good to me. Need X in there? There should be some values. Really around everything, which around here doesn't matter, because that's about matters. Still good here? Still good? You're still good here? Did you not like this thing? You can put it like put them together as one thing to the end. Still good here? So this it becomes 1/5 X. Okay, yeah. And then you make it a 5. Yeah, that's good. I don't remember. Something like that. All right, folks seem to be doing pretty well here. Can we chat about this one? So I'm going to find the interval of convergence. You begin with the ratio test, the RAT. I go L equals, and you know, it's fairly routine, but you gotta make sure you don't screw it up. So I begin with the n plus 1 power, x to the n plus 1, over n plus 1, 5 to the n plus 1, and then I multiply by the reciprocal of the original term, n, 5 to the n, minus 1 to the n, x to the n on the bottom, like that. And now I'm going to simplify. Let's put, sorry, I forgot to write lim. Let's put together all of the similar parts. So I have minus 1s. I have 5s. 5 to the n over 5 to the n plus 1. I have the stray n's, n over n plus 1, and I have the x's. And you need absolute values around all of those things, although most of these absolute values don't do anything because what's inside is positive, but you need them. Now simplify. The first one inside the absolute value is just -1 because here I have an extra -1 on top. Here I have an extra 5 on the bottom, so the next one is 1/5. The next one is what it is. I mean, eventually in the next step I'll take the limit of that. And then the last one is just x inside of absolute values. And now we do the lim. The n over n plus 1 becomes a 1 because that's the limit of that ratio of polynomials. And then absolute value -1 is just -1, is just +1. So this just gives me 1/5 absolute value x, right? That becomes a 1, that becomes 1/5, that becomes a 1, and then this has to just stay what it is, absolute value of x. All right, and so I say the interval of convergence, well, this is not my final answer, but it converges when 1/5 absolute value x less than 1. This is the same as saying -1 less than 1/5 x less than 1, which is the same as saying -5 less than x less than 5. All right, and this is sort of like the first half is done. Maybe it's a little more than half. Right? So it converges in this interval. We need to check the endpoints as special cases. So we check the endpoints. Let's check x equals 5 first. I write my original series, but I plug in 5. So it was -1 to the n, 5 to the n, over n, 5 to the n. And then hopefully this will simplify and just end up looking like a standard thing that you recognize. I cancel the 5 to the n's straight up, and we just get -1 to the n over n. This I recognize as the alternating harmonic series, the alt-harm, which converges. It actually converges to ln of 2 or whatever, but it doesn't. I don't care about that specifically. This one converges at x equals 5. And then x equal -5, I go sum -1 to the n, -5 to the n, over n, 5 to the n. All right, this one's a little strange up top. How do you simplify -1 to the n times -5 to the n? I would combine it into a single nth power like that. And then we can, you just multiply those. I get -5 to the n up top, divided by n times 5 to the n. This can cancel by, what? Sorry, it's not negative anymore, it's positive. This is, I multiplied them, right? So it's I meant to say -1 times -5, right? This, I forgot what I was doing. That makes it 5 to the n, and then that cancels completely right there. So this is 1 over n. This is the harmonic series, not alternating, which diverges. All right. So my final answer then is this interval, but it converges on the left side. So I include the left endpoint. So the interval of convergence is closed bracket at -5, open at +5. I hope that's what everybody got eventually. There's kind of a lot of steps to these. It'll take you a few minutes, although they pretty much all go the same way. You do the ratio test, and provided that you do all of your simplifying correctly, you end up with this interval. You have to check the endpoints, but hopefully they work out easily also. All right, great. I hope you won't mind, I think I want to leave it at that. You know, when I was looking at the calendar, I also realized, even after canceling a day, I think I can give up 20 minutes today. So that'll do. Let me know if you want to hang around and talk about the homework. If you've got questions, I'm happy to talk about it.